everyone. So this video is basically just going to be a continuation of what we were talking about in yesterday's video. So we're going to see two new methods, algebraic methods of simplifying functions to allow you to evaluate a limit. So first, just want to start by reminding you of the two important facts that we talked about in yesterday's video. That will kind of, like, these are the two facts that really underlie the methods that we used in yesterday's video and then in today's video. So the first fact is that if f of x is a nice function, oops, I forgot the word if f of x is a, and I'm just going to put nice in quotes here. When I say a nice function, I just don't want to list out that really long list that I did in yesterday's video, but I'll make a note here. So there's a list in the previous video of all the different types of functions that are included. Basically, if it's not a piecewise function and it consists of the types of functions that you've learned about in pre-calculus, then it's considered a quote-unquote nice function. So if f of x is a nice function and f of x is defined at x is equal to a, then you can evaluate the limit as x approaches a of f of x by just plugging a into your function. So like I said in yesterday's video, usually if you're taking a limit, you're not really going to be in that situation because the whole point of limits is to enable you to talk about situations when the function is undefined. However, that first fact is going to be really important because basically it allows us to take a function that is undefined, simplify it, and then plug the number into that new function that, is defined. So the second fact is that if f of x and g of x are two functions that are identical everywhere, except at x is equal to a, then the limit as x approaches a of f of x is going to be the same as the limit as x approaches a of g of x. Because remember, it doesn't matter what's happening when you're taking a limit at that particular x value. It matters what's happening around it and where the graph is kind of heading. And so the idea is that if you start with a function that is undefined and you simplify it to the point where you kind of get rid of that issue in the function, your new function will be identical to the first function except for at that one value where the original function was undefined. And so by simplifying, you'll get yourself into a situation where you can then go use rule 1 and just plug a number in. So maybe I'll kind of summarize that, and then we'll look at, I'm going to list out again the different algebraic methods that we'll be using, and we'll look at the second two that we didn't get to in the last video. So basically, your goal when evaluating limits is to simplify the original function f of x to get a function g of x that is defined at x is equal to a. And then once you do that, you can just plug x equals a into g of x, into the simplified version. Okay, so what were the methods of simplification? So there were two that we talked about. Simplification, sorry, I'm having trouble spelling right now. Simplification, that's an A. Methods. So the two that we talked about in yesterday's video, one of them was factoring and canceling. And so without actually doing this problem out, I'm just going to write down a example of a problem where you would use that method, just kind of for your own reference. So if we were trying to take the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2, that would be the type of function where the simplification method would be factoring and then canceling. So basically, if you have a polynomial in the numerator and in the denominator, and especially if you can notice that there might be a common factor between them, that's when you want to use this factor and cancel method. So the other method we talked about in yesterday's video is expanding and simplifying. And so this is going to happen when you have a part of your function that basically can be multiplied out. And you'll see that once you multiply it out, that's what enables you to actually cancel something from the denominator. So an example of that would be something like the limit as x approaches 0 of 5 plus x squared minus 25, all divided by x. Okay, so third method that we're going to be talking about now in this video is multiplying by the conjugate. And so we'll talk about what that means in a moment. But I want to first just kind of show you the type of example where you're going to be using this method. So you're going to be multiplying by the conjugate basically in any circumstance where your limit involves a square root. So a typical example, and we'll do this one actually later in the video, would look something like this. So the limit as x approaches 0 of the square root of x squared plus 9 minus 3, all divided by x squared. So basically we'll see that multiplying by the conjugate allows you to get rid of a square root, and in doing so will allow you to see some simplification that can happen. And then the last method is making a common denominator. And so, as you might guess from the idea of making a common denominator, this will happen when you have a function where there's multiple fractions involved, or there's a fraction that you want to add to another number. And so an example of that would be something like this. So if you're trying to find the limit as x approaches 1/2 of 1 over x minus 2, all divided by x minus 1/2. So again, we'll do that specific example in this video as well. Okay, so before we get into multiplying by the conjugate, we have to kind of talk about what the conjugate means and like why it works the way it does. So this page, we're going to be talking about multiplying by the conjugate. So before we even get into that, we'll see that the idea of multiplying by the conjugate basically is just an example of a difference of squares. So I want to remind you what a difference of squares is. So an expression is called or let me say it this way, an expression of the form a plus b times a minus b. So what happens when you multiply two things like that together, where you have basically the same two terms, but one of them has addition and one has subtraction? When you multiply those two things together, you get a squared plus ab minus ab minus b squared. And so these middle terms cancel out, right? So you have a plus, you have a minus, and altogether you're just left with a squared minus b squared. So anything that is of this form is called a difference of squares. And so we're basically going to take advantage of this, this nice property of like these middle terms canceling out to help us get rid of square roots. Okay, so let me define for you what the conjugate is, and then we'll look at some examples. So the conjugate of an expression of the form square root of A. And here we'll see that when I'm using a capital letter A because really what the stuff under the square root, it could just be a number, it could just be x, but it might actually be a more complicated expression. So like, for example, this one here, right? We had square root of x squared plus 9. So I'm using a capital letter A to basically represent like any algebraic expression could be under this square root. So if you have something of the form square root of A plus square root of B, and we'll see that when you're working with conjugates, you don't need to have two square roots. One, you could just have something where one of them is a square root. So we'll look at examples in a second. But so the conjugate of square root of A plus B is square root of A minus square root of B. And so the important thing is that when you're finding the conjugate of an expression, you're just taking the plus symbol and changing it to minus, or if you started with a minus, you're changing it to plus. So you're just switching that sign. So why is that a thing? Why are we even talking about conjugates? Well, because if you take these two expressions and multiply them together, it will be a difference of squares, and so stuff will cancel out. So if you multiply an expression by its conjugate, the square roots will cancel out. So let's just kind of see that in action. So if you had, again, the square root of A plus square root of B business, so if you did square root of A plus square root of B times square root of A minus square root of B. So this is a difference of squares, right? So we don't even need to write out every single part of it because we know that the middle terms are going to cancel out. And so because the middle terms are going to cancel out, we're going to be left with square root of A times square root of A, or square root of A squared, minus square root of B squared. And if you take a square root and square it, it just becomes the stuff that was inside the square root. So you get A minus B. Okay, so let's look at some examples. And so basically, maybe just to tell you how this will be useful, it will then allow us to get rid of square roots in these limits that will then allow us to simplify things in a different way. Okay, so an example. So let's try to find what is the conjugate. Sorry, for some reason my touch screen on my tablet is a little, just doesn't want to write smoothly right now. So let's say we're trying to find the conjugate of the square root of x minus the square root of 5. So all we have to do is take this negative sign and change it to a positive sign. So the conjugate would be square root of x plus square root of 5. And so what happens when we multiply them together? So if we multiply these two things together, we don't even really, like the whole point of going over this is that I don't want you to feel like you have to multiply it out by hand every time, because if you recognize the pattern, basically what's going to happen is you're just going to be multiplying square root of x times square root of x, and so that gives you x. And then square root of 5 times square root of 5 gives you 5. So you can totally, put the two next to each other and do FOIL or whatever you want, but the whole point of this is recognizing that when you have a difference of squares, the middle terms are always going to cancel out, and so you're just going to be multiplying together this times this, and then this times this. Okay, so one more example before we get into an actual limit. So let's try to find the conjugate of square root of x plus 4 plus 3. So this is an example where we only have one square root, but that's okay. It doesn't matter. As long as there's one square root in there, you can still find the conjugate. So what would be the conjugate here? Well, all we want to do is change this plus sign to a minus sign. So a really important thing, I'll write out what the conjugate is, and then I'll just tell you what the conjugate isn't. So it's really important that you're only changing the sign that's between the two things that are getting added and subtracted. So it would not be correct to say the conjugate is square root of x minus 4 minus 3, or square root of x minus 4 plus 3, or anything. You don't want to be changing that plus sign. You're only changing the sign that's kind of joining the two terms together. So if you were to multiply these together, you would find that their product is going to be x plus 4, so that's what you get by multiplying the two square roots together, and then minus 9. And so altogether you would get x minus 5, which I actually didn't intend for that to be the same as the previous one. So that's just kind of a coincidence. I don't want you to read too much into that. Okay, so let's actually do an example now of how we can use this to evaluate a limit. So let's say we're trying to evaluate the limit as x approaches 0. So this is going to be the same problem that I wrote down earlier. So square root of x squared plus 9 minus 3, all divided by x squared. So first of all, I think it's worth mentioning, like, why do we even need to use algebraic simplification here? Well, we can't plug in 0 for x, right? We would get something that's undefined. So it's always a good idea, before you jump into whatever your algebraic methods are that you're going to use, double check that can you plug in the number? And you can't in this case, right? Because you would get divided by 0. So first we need to figure out, what is the conjugate of this thing? Because that's what we're going to multiply by. So the conjugate, like we saw in the example just previously, we're not going to change the sign inside of the square root. We're going to leave it as square root of x squared plus 9, but then we're going to change it to a plus 3. Okay, so there's one essential thing that I haven't really said yet, which is when we go and multiply, you can't multiply just the numerator by something, right? Because we want to simplify this expression. We don't want to make it like a completely different function. And so what we need to do is multiply both the numerator and the denominator by the conjugate. So if you multiply just the numerator, you would, we are changing the function by simplifying it, but that would be making it like a completely different function. And so this wouldn't work if you just multiplied the numerator. So we want to multiply by, sorry, this keeps sliding up. So we're going to multiply by the conjugate over the conjugate. So we have the limit as x approaches 0 of the square root of x squared plus 9 minus 3 over x squared. And we're now going to multiply that by the square root of x squared plus 9 plus 3 all over the square root of x squared plus 9 plus 3. And so one thing you might notice is that we are going to simplify the numerator. The denominator is actually going to become more complicated, but it will be okay because we'll see that just the way things pan out, the way the simplification is going to go, it will enable us to eventually plug in 0, which is the goal. Okay, so what do we get when we multiply these two things together? Well, in the numerator, we have seen what the pattern is, right? So the two things under the square root, the square roots will cancel each other out. And so that will become x squared plus 9 is what we get for the first part. And then we multiply the second two things together and subtract that. So that's minus 9. So that's, again, just following the same pattern of the difference of squares. Maybe I'll even put this in parentheses just to emphasize where it came from. So that came from the square root, the 9 came from the other part. And then in the denominator, this is really important. Don't multiply things like out. Like you want to just leave it like this. And just trust that eventually you'll be able to simplify something, and you're actually going to make it a lot harder to see what can be simplified if you start multiplying in and distributing. So just leave this as is. I'll even make a note of that. So don't multiply this out. or I'll say don't distribute, right? Don't distribute that x squared, just leave it as is and trust that things will work out. Okay, so now we have the limit as x approaches 0 of, so the numerator is x squared plus 9 minus 9, so that's just x squared. And then in the denominator, we have x squared times this stuff, so times the square root of x squared plus 9 plus 3. And so now we can see that there's a common factor in the numerator and the denominator, right? So we have an x squared up here, we have an x squared down there, and we can cancel those out. And so that's why you didn't want to distribute, because it, and in some cases I think it'll make it even harder than it would here to see what you can cancel out. So what are we left with? Now we have a 1 in the numerator, right? So it's really important to realize that when you're canceling a common factor, if that factor is all you have in the numerator, it doesn't become 0, it becomes 1, right? It's like if you have like 5 over 5, that's equal to 1 over 1 or 1, right? So, so we have 1 over square root of x squared plus 9 plus 3. And now we can actually plug in 0, right? Because we don't have that x squared in the denominator anymore. Even at this previous step, even over here, we could not have plugged in 0, right? Because we had an x squared in the denominator, but now we don't. And so now we're at our new simplified function and we can just plug in 0. So we can just do 1 over the square root of 0 plus 9 plus 3, which is equal to 1 over, so the square root of 9 is 3. So we have 1 over 3 plus 3, and that altogether gives us 1 over 6. So this is the only example we're going to do in this video of this type of problem, just because they are all really similar. So, as long as you know how to find the conjugate, make sure that you're multiplying by the conjugate over the conjugate. I think that's a very common error, is that people will forget to multiply in the denominator. You should be good on these. And let me show you the graph just so that we can see, again, that idea of what it looks like to simplify these functions. So this is like a surprisingly boring looking function. I would expect f of x equals square root of x squared plus 9 minus 3 over x squared. I would kind of expect that to look a little more interesting than this. It almost just looks like a horizontal line, but it's not, right? See, it kind of like peaks up a little bit in the middle. But yeah, so the important thing with the original function is that, again, it's undefined at 0. And I'm not sure why it's jumping down there, but we can see that it's undefined, right? So if we simplify it, this was our simplified version. It was 1 over x squared, square root of x squared plus 9 plus 3. And notice it looks exactly the same. It's just that it does not have a hole at 0 anymore. Okay, so one more example we're going to do in this video is now going to be about making a common denominator. So basically, the idea behind making a common denominator is that when you have two fractions that you're trying to add or subtract to each other, you have to make a common denominator in order to do that, right? So let's say that, let's look at the example that I had written earlier. So the limit as x approaches 1/2 of 1 over x minus 2, all divided by x minus 1/2. So yeah, so basically we're going to, in the numerator and in the denominator, make a common denominator among what's there. So what would be the common denominator in the numerator? Well, the only real option is x, right? We have already 1 over x, and then we just have 2. And so we want to make 2 have that same denominator. And so the way we do that is we multiply by x over x, right? Because when you're making a common denominator, you want to make sure that you're not changing the value of the number. So you have to multiply by something over itself. And so we're multiplying by x over x to give us that new denominator of x so that we can combine it with 1 over x. And then similarly in the denominator, we have x and then we have 1/2. And so the common denominator is going to be 2. And so we want to multiply x by 2 over 2. Okay, so let's see what that gives us. So we have the limit as x approaches 1/2 of, and I'll just write out this intermediate step with the new denominator. So we have 1 over x minus 2x over x. So we have the same denominator now. We'll be able to combine them. And then in the denominator, we have 2x over 2 minus 1 over 2. So now let's combine these fractions. And so in the numerator, we'll have 1 minus 2x over x. And I forgot to write my limit, so let me not forget that. So we have the limit as x approaches 1/2 of 1 minus 2x over x, all divided by 2x minus 1 over 2. So the next step that is a really important algebra trick to know, and I've definitely tried to emphasize this in some pre-calc classes, is that when you have a fraction divided by another fraction, so like this, you can rewrite it. So if you have something that's like a over b over c over d, that's the same thing as a over b times d over c. So you're basically taking the reciprocal of the denominator and multiplying with it instead of dividing by it. And so that's kind of the whole point of making the common denominator, is that now we just have fraction over fraction, which enables us to use that simplification trick. And we'll see that that will allow us to further simplify the expression. Okay, so we have now 1 minus 2x over x, and we're multiplying that with 2 over 2x minus 1. All right, so there's one more kind of trick that we need to use here. So you might notice that what we have here and here, they look really similar, and you kind of want to cancel them out, right? Because it would be really nice if we could cancel those two things out. And maybe let me just take this opportunity to point out that we still can't plug in 1/2, right? Because if you were to plug in 1/2 in the second denominator, the 2x minus 1, you would still get 0. And so you would still, as long as you have a 0 somewhere in the denominator, it's still an issue. So how can we cancel these two things out? Well, you should recognize the fact that basically if you have two things being subtracted, but subtracted in the opposite order, they're equivalent to each other except for a multiple of a negative sign. So what I mean by that is that in general, if you have a minus b, that's going to be the same thing as negative b minus a. Sorry, I wrote this not the way I want to. Let me just try to find a better space to put that. I'll put it here. So a minus b is the same thing as negative b minus a, right? Because if you were to multiply that negative sign back in, you would get negative b plus a, which is the same as a minus b. And so what we're going to do is we're going to take one of the two things that is circled in purple, and it doesn't matter which one you do it with. I think, let's see, in my notes, I did it with the second one. So I'm going to leave 1 minus 2x the same as it was. And actually, let me go below because I think I'm going to run out of space a little bit. So if we leave this one the same, 1 minus 2x over x. But now we're going to rewrite this second one as 2 over, and we're going to factor out a negative sign. And so once we factor out the negative sign, we have negative 1 minus 2x, right? Negative 1 minus 2x is the same as 2x minus 1. Just if you multiply the negative sign back in, you'll have negative 1 plus 2x, which is the same as 2x minus 1. So now we can cancel these out. But the important thing is we're left with a negative sign, right? So this is going to go away, this is going to go away, but we're going to be left with a negative 1 in the denominator. And so this is going to give us altogether the limit as x approaches 1/2 of 1 over x times 2 over negative 1, which is the same as the limit as x approaches 1/2 of 2 over negative x. And so now we can finally plug in 1/2, right? Because we now no longer have any issue with plugging in 1/2. And so if we plug in 1/2, we get 2 over negative 1/2. And so again, we have to remember that dividing by a fraction is the same as multiplying by the reciprocal. So 2 divided by -1/2 is the same as 2 times -2/1. And altogether, that gives us -4. So again, I want to take a look at the graph just to show you what was going on here. So here's the graph of the original function. And we're taking the limit at what? At 1/2. So if we go to an x value of 1/2, we should see that it's undefined there, if I can hit the right point. Yes. So it's undefined at 1/2, at 0.5. And then we simplified it, and the simplified version looks like this. It looks exactly the same. So -2/x looks exactly the same as the original function, but now there's no longer a hole at 0.5. So we were able to actually, and we can see, right, the y value is -4, and that's what we got. All right, so that's it for this video. I really encourage you to do the examples on the worksheet, just because there are a variety of ways, especially with the common denominator. There are different kind of ways it can play out, and I think it's really important that you get to see those different examples. So please do the worksheet, read through the solutions, and I also encourage you to graph these functions and the simplified version, just to kind of show yourself how they compare and start to get a sense of how different the graphs of different functions look. All right, I will see you all in the next video.